Chairman of TC101, Professor Erdem Ibrahim from University of Bristol.
Thank you. Good morning. I'd like to open the first session of the workshop with a keynote lecture presented by Professor Nilo Consoli on liquefaction, on the use of fingers to avoid tailings liquefaction. I'd like just a few words of introduction of Professor Nilo Consoli. Professor Nilo is Professor of Civil Engineering at the University of Rio Grande do Sul, one of the best institutions in Brazil. He graduated from the same institution in 1985, and he obtained his PhD at Concordia University in 1991. Professor Nilo is not only a very prolific publisher research with more than 200 papers, but his research on ground improvement, artificially cemented soil, fiber-infused soils, offshore and onshore foundation is often at the forefront of new discoveries recognized by prizes, international prizes. He is serving as associate editor and as editorial board member for a series of top international technical publications. So, Professor Nilo Consoli, so please.
Thank you very much, Professor. Thanks to for an invitation to really true to everybody from Cyprus, and so it's an honor to be here. And I want to present to you some experience that we have in Brazil regarding tailings disposal, the static liquefaction that we have had, and the possible solutions that are being looking at, and that we are doing some research in order to see if we can find novel, as I said, novel ways of getting stabilized these materials without problems that we have had, like 2 huge failures with more than 300 people were killed in the last few years. And I'm going to show you something regarding the problem and the ways that we are trying to look how to solve it. The problems that are already in, just for you to have an idea, we have about 800 upstream dams in Brazil, that we have a lot of them that have they are realizing not the safety factor is nearly 1. So we have to decommission all of them, and the size of it, there is a law that was introduced after the last failure that killed 250 people or more, that it's forbidden from 2020 and on to raise new upstream dams. So this, as I said, we have 800 and we have to decommission them, and we cannot build new ones. They are the cheapest, and so that's why it was used, but now it's not possible anymore. That's the reason that I'm going to present to you the problem and possible solutions for new disposal of new material and ways to decommission also these tailings that still are with some problems. Okay. Just also to tell you, which is interesting, if you wish any kind of contact with me, that's my email, and I would love to respond or get in contact with anyone. So it's consoli@ufrgs.br. Okay. The first thing, just for you to have an idea, I have some experience with tailings dating 30 years ago in my PhD in Canada. in which the problem that we had at that time was completely different than the one that we have nowadays. At that time, we didn't know how to manage about the volume of tailings that we could dispose behind a dam and a reservoir. So at that time, my PhD was regarding this kind of solution, a numerical solution. So I worked in the development of a constitutive model based on the critical state solid mechanics with a former student of Rusko from Cambridge, Professor Purshad. That's why even I have chosen the university to work with him. And he was the one that started to look at sandy materials from the critical state solid mechanics side. Because, you know, Schofield, Rolf, and all the others, they look mostly to clay materials. And then he was looking, that's one of the reasons, because the tailings, you have silty and sandy material at that time. So, and I went after to solve this problem, as I told you. And in the end, I have published a paper. It was basically a real problem that we have with bauxite tailings that this slurry was disposing some point like here, and it starts to be taken by the water, and so you have sedimentation and also consolidation, everything occurring at the same time. Bring it back. So we have to solve it numerically. At that moment, we didn't have, even nowadays, you don't have an analytical solution for it and such and so. So I have to develop two codes, one in finite difference to deal with the conduction of the sediments, the sedimentation, and after large strain consolidation and whatever. So using BO's theory and whatever, except of course, everything numerically speaking. So I did that, and I published a paper after some more studies with during a period that I was at Oxford working with Professor Gillian Sills. She was an expert also in sedimentation and such and so. And my first paper was published in Geotechnique at year 2000, and I was lucky to get even a prize for this paper, which was fantastic when I started having just to have it recognized as a good solution for the problem. Just for you to have an idea, when we're dealing with this bauxite tailings, these dots are results of the void ratio with depth. And the solution, it was a three-dimensional solution, but in the end, in one point, we got this dashed line here as the numerical solution of the final void ratio. So it started with a void ratio of 6 in the top, and it ended with void ratio about 3. So we are dealing with a pretty problematic material if we have any kind of quakes or so, which is not common in Brazil, but even static liquefaction, what we did already in the last period, we might have problems with this kind of high void ratio and such a material. But what is interesting also to see here is that due to transport of the material and just sedimentation, we could solve the problem saying that we have a possibility of putting like 500,000 tons of material behind a dam in a reservoir. But if you consider the consolidation, the real consolidated height, considering small, large strains and Eulerian or like Lagrangian viewpoints and so, it almost doubled, and that was what really happened. Almost double the amount of material that you could put behind that dam, really. But as I said, this is just the first point that we have had. But recently, as I told you, and this I brought just for you to take a look. This is iron reservoir it was raised with the upstream way. And in 2019, we have had the failure. So these are just the sequence of it. And in this one, we have had more than 250 people killed. And that's everything changed from that moment and on in Brazil. Because of that, even if possible, there's a link here where you can see the video of this failure. So I just took some pictures to show you what was the problem that we have had and why it is forbidden in Brazil to do such a disposal from then and on. So as I said, we had to start thinking about novel ways of solving the problem. And so at that moment, Vale, which is the biggest mining company that we have in Brazil, they approached me at university because they wanted to look for solutions using dry stocking, which means you filter the material, the slurry, you get it to a certain moisture content, then you compact in layers, and then you can do, as they expect, these dry stocks up to 300, maybe 400, even 500 meters high. So the problems start in such a situation because, let's say, I start compacting in the bottom. When I get it to 300 meters high, what's the pressure that I'm going to have in those materials? Is it going to be the breakage of the grains? If it does, is it going to have some change in the critical state solid mechanical parameters due to that? So all of this stuff is still not well known, mainly for this kind of man-made materials, let's say these tailings that they are non-plastic and they have their own characteristics, even though you might have even some small particles with clay size or something like that. They are not clay minerals, so they do not have the plasticity or whatever that you would have. So it's different from the natural material, and we have to look at deeply about the basic behavior in order to be able to solve this problem. And there were also some questions regarding this this filtration and compaction, and in the end to go for this dry stock up to 500 meters. And I told them we should look at two different thoughts, at least in the beginning. One is just the idea of, as they used to say, filter and compact it and getting to the height that you desire and so. But then there's also a possibility of putting some cement, adding some cement on it and starting to compact and going up. Of course, that depending on the amount of cement and such and so, and the height of stresses that you're going to have due to the raise of this stock, you might have the breakage of the bonds of the cements that are staying below. And as I said before, you might have the breakage of the particles, the sandy particles mainly. So this is still something that we have to understand better how it's really going to change due to these particularities that we have for such a solution. But I'm going to show you some of the problems that we are already starting to look at for this solution. The first problem is a practical problem that was recalled for us, which is like, okay, do you have any problem due to compaction? For example, might you have some breakage of the particles, sandy particles, due to high energy, because the equipments that are supposed to be used in the field, and they are already doing it, have huge energy and high frequencies and such and so on. Would that make any difference, I mean, regarding possible break of the particles or things like so? We are studying that, and we have done some tests for two different equipments, but we have done in the lab and also in the field to check it out. And for example, in this case here, we have a 22 tons vibratory roller compactor for compacting up to 50 centimeters. And in the other case here, you have an impact roller to compact thicker layers and also see if what is going on to happen. So this is an ongoing research that we are doing, but just to show you, this has not been shown before. We're still writing something about that, but at this moment, for example, for iron ore residues, tailings in this case, we could not find the breakage of the particles due to this compaction, applying the energies that we might have, cyclically or not applied, let's say, up to reasonable pressures that you might have. These particles that are mainly silica, sand, and such, and so they do not break. However, we got much higher pressures than the ones that you might have in the field. And then, yes, you do have breakage, but that's not real. I mean, we have even to check it out if it was going to occur, which were the pressures to do so. But the good news for Vale, which was the one that they were paying for this research, is that for the usual pressures that you get from these equipments, you don't have the change of the size of the particles due to compaction for this material. This is something good technically for them. Okay, but what about if we are looking at, as I told you, real high pressure due to the stocks being for 300, 400, or even 500 meters high? What's going to happen for the material that is below when you are raising it? And this is something is also hasn't been shown anyway. It's just anywhere. It's just a initial result here, in which we have the two different pieces of the material. One is like both come from iron ore tailings, but they are retrieved from the process in different moments. And you have one of them that is mainly silt, and the second that is mainly sand. And we apply isotropic stresses up to 120 megapascal, of course, much higher, at least 10, 20 times higher than the ones that we are going to have, even with a 300, 400, 500 meters high stock. But just to have an idea what's going to happen. And for the silty material, even reaching 120 megapascal, we did not have any breakage of the particles. Okay, but when you do have mostly sandy materials, from a certain point, as I said, just applying confining stresses, I'm not shearing at this moment. And you do have the breakage of the bonds, as can be seen here. These on the top are almost are the results for the silty material, that they are similar before and after applying such a high stress like 120 megapascal. But here in the bottom, you have the materials that were compacted initially in a dense way or in a loose way, and they both have you have the breakage of the particles, and so you have smaller size particles and so. And we are looking, of course, at the real situation too, and that's something that's still ongoing research. But as I told you, the concept that we have in Brazil, which differentiates from 2020 and on, is this idea of using dry stock. And in such a case, at this moment, they have already decided that we shall go at least to 300 meters high in stocks, which, as I told you, we have some specific knowledge that still not has to be studied. There are some points that have to be clarified about possible particle breakage and other points that you might need to understand it all. Here is a paper that was just accepted at Geotechnique. It's still not printed, but it's going to be soon ahead of print, in which we have a decommissioning kind of problem. So this is a reservoir for a copper tailing, and we have got specimens from, here's discharge point, from what we call upper beach and from the lower beach. Of course, the difference is basically the size of the particles that in the lower beach due to the transport of sediments, such and so they are smaller size than these ones that are in the upper beach, which is interesting that we see here just the difference. Both are silty sands, but they have some differences in the amount of silt, basically. Here we have plenty of results, drained and also undrained, and we have analyzed these results for, in this case here, is just for the upper beach material. We have made the decision of looking at 3 different compactions energies. So we have different densities of initial voice ratio. So in 3 different ways, and we want to look at the influence of the voice ratio regarding liquefaction or things like that, what is going to happen, and also through the base of the critical state soil mechanics viewpoint. What's going to happen? Okay, this is just the isotropic results from these specimens that these on the top, they have a voice ratio compared to about, if I'm not wrong, 85% of the maximum density, and we have, these are just the isotropic points in the beginning of the shear before shearing it. So what is interesting is that this is for 86% of the energy that is applied, so a lower density. This is an average density which is 91% of the maximum density, and this one is for 95% of maximum density. Anyway, we have 3 different straight lines. At least we have approached to this. These are for all results from, as I said, from 86, 91, and 95% of maximum density. The critical state line can be reached nearly by a unique M, as expected in this QP dash space. But the differences that we found out in this case are going to be shown in the next slide. This next slide is interesting because it is showing that depending on the initial condition of the specimen, we do not reach a unique critical state line, which not exactly conventional, but that's what happened in this case. In this case here, I'm showing you just the results for the upper beach tailings. We have also in the paper the results for the lower beach, and they show similar tendency, which means the final results, the final critical state line in this specific volume, mean effective stress space, depend on the conditions of the compaction. As I said, this was not necessarily expected, but this has been found before for other materials. And in this case, we found out this, and we have done several tests, specific tests, to confirm that, so we can guarantee that this is really what happened. And we have tested some other also iron ore tailings. This is copper, and for the iron ore tailings we did similar tests, and this did not happen. I mean, you get to a unique critical state line in this space for those materials. So you it depends on some characteristics, grading, and some other mineralogy and such and so on the material together, not to such a condition. But it's interesting to see that that happens for this one. So things might not be so, let's say, basic as we expect, and we have to search further in this case. Okay, as I told you, another possibility that we are looking at is to add some cement to this tailings dry stock, and to see if they are going to be, I mean, we can do steeper embankments and such and so to have a higher volume and have even, of course, higher safety factors. We are studying the, as I told you, the breakage of the particles, but in this case also the possible breakage of the cementation during the raising of the tailings. We are looking at all of that. And in this case, you can see mostly from now and on, you are going to see in the bottom the papers that are the link of the papers that were published talking about this. This is a paper that was published in the beginning of this year. So this is the things that I'm showing now are brand new, and some reviews that were not even published yet. But in here we have the concept here in the top of the upstream dam. That's not possible to do yet anymore because of the failure that we have had. Here you have this blurry deposit and so on. And here is the concept of doing layers of compacted materials. In the first I told you the idea of doing so without any cement, just compacting it, and here adding some cement. Just to have one specific view, this figure here, we have a material in the same, with the same vibration, just that this one that we have here with this huge volume change, compressive volume change that we have here, is the material without any cement. So these are drain triaxial tests, but if you do the undrained, they are going to liquefy statically, that one. And we have had, but keeping the same void ratio, we add 3% of cement regarding the amounts of the weight of just the solids, and then you change completely the view to something that is stronger, stiffer, but brittle. So there is a problem in the end with the brittleness of the material. But you see here in the bottom that it stops basically the reduction of the volume, and you even have some dilation on it. These are, as I said, drain tests. Here's something that I know that Abdullah and some of the people here from Turkey and Cyprus and some other places in the world are already using. And as I'm going to talk a little bit about the cementing the material, it's just interesting to show something about this, the concept of this index, that it's porosity divided by what we call the volumetric amount of cement, the CID. We call it that. It started with some research in the middle of the 2000. This paper here for 2007 is the most cited paper that I have. It was published as Journal of Geotechnical and Environmental Engineering, and at this moment it has 313 citations at Web of Science. And what I'm going to show you now is that this index control what's unconfined compressive strength, splitting tensile strength, initial shear modulus, bulk modulus, initial bulk modulus. It controls peak of triaxial tests, the value of it. It controls durability of the loss of mass. It controls the expansion of clay that has some expensive minerals on that. It also, we can control the amount of expansion that you might have to this index. Here are just some basic ideas that we have. just the concept on how to look at it. For example, here are several energy of compaction. We can make some molds in several points. We get the function, for example, of with several amounts of cement, function of porosity, the strength and confined compressive strength due to porosity with different amounts of cement. But in the end, what we show that with that index, the unconfined compressive strength can get to a unique line. Okay. Here it's a joint work that was carried out with between University of Bristol with Professor Erwin Ibrahim, Professor Andrea Giambra, myself, in which the study was like to have some analytical base for that index that shows that, because we knew it experimentally that was working. But then with these and some other further works that were published from 2017 and on, we have the analytical proof for why that index controls really these cement tissues, materials. But I'm not going to enter in details, but that was, as it's shown here, was published also at the Journal of Geotechnical and Environmental Engineering in 2017. This is a paper also from the Journal of Geotechnical and Environmental Engineering from 2010, in which it was the first time that we showed that the unconfined compressive strength and also the tensile strength, split tensile strength, you could get unique curves using different void ratio, different amounts of cement, but you would get a unique curve for unconfined compression, a unique curve for tensile. And if you get these curves and divide the equation one to the other, you get a scalar that is unique and doesn't change with the amount of cement or the density. So it's quite interesting. So as I said, it was published in 2010. Let's go on. This is a paper that was published in 2012 at Geotechnique, in which we introduced the first time the concept that the initial shear modulus that would be measured through bender elements or through ultrasound equipment, depending where you are doing it, it also is dependent on this eta CID kind of index. So you have for different materials, these were sandy material from Brazil, and this was a sandy material from Portugal. They have been tested by different people, but as I said, you have a unique curve for one material with one cement, and for the other you have another curve. But each curve is, as I said, is controlled by this index. Here is something also interesting that was published in 2009 already, showing that if we have, for example, these triaxial tests that they were molded with different void ratio, different amount of cement, but the same eta CID, the same index, they have, these are, let's say, with under a specific confining pressure, they have the same behavior from beginning to the end. I mean, you can see the whole curve that is the same, even though, as I told you, the void ratio and the amount of cement of both specimens are different. However, they have the same index. This is also something that was published at Journal of Materials in Civil Engineering from ASC in 2017, in which we have shown 4 different granular materials. Some are man-made, some are real ones. For example, this is a part of material from Porto. This is Osório sand from Brazil, and these 2 materials are recyclable parts of the polishment of agate, which is a kind of a stone, and also some materials based on the rest of crushed basalt. But anyway, they are all sandy size kind of particles, but they do have, as we can see here, quite different angularities and roughnesses too. Okay, but we have tested basic tests as unconfined compressive strength and splitting tensile for these materials, and each one of them we have used different cements, different amounts of cement, different densities, such and so, and each one of them, of course, we can see here some results, as this green one here are the results for several amounts of cement and several densities, and just the splitting tensile strength, we can get this unique green pure. And the other pure, the red one, the blue, magenta, and so other materials from those four materials with different amounts of cement. And as I said, this green one is unconfined, it is splitting tensile, the others are unconfined compressive. What we did here, just to have a kind of possibility of normalizing it, we have divided each one of these curves by the result that we have of the QU or QT, which are the unconfined compressive strength or the splitting tensile strength for eta CID 20. So we get 20, see where it beats the curve gets here, and divide the whole curve by that. Doing so for each one of these and much others, we get a unique curve for different sandy materials that I show you, with different roughness, different shapes, and so on, which is interesting for practical reasons, because in the end, we can show that we have, a unique equation, normalized equation here, that if you have, in the end, carried out one result, for example, with a specific porosity and a specific amount of cement, you can get the whole curve doing at least one. Of course, you usually repeat it 3 times to have an average for that, but we can, because the shape of the curve does not change. That's quite nice for practical purposes. So we have similar things for clay and silty materials here. That was published at Soils and Foundations. It's previous, sorry, preview. Let me come back. Okay, this one here was for sandy materials. This one was for silty and clay materials, was published at Soils and Foundations, 2016. These are just examples in which I just have one point, for example, this one blue here in the top, and I could draw the curves, and all these other points are lab results that we carried out later. They were not used to fit this curve. We just have one point, and then the others fit really the curves. This is for another material, gold tailings, and this is for coal fly ash tailings, just to have an idea. So this is a paper that I'm bringing back from previews that was published in the beginning of this year, in which we have shown, here is a kind of, not a good picture, but we have here curing periods from 2 days to 90 days. And also we have 3 different dry densities used, and we have a fit for each and every curing time, and they show the same curvature. The only thing that changes is scala in front of the equation. So this is for results for several. Each one of the curves is for a different curing time, but the unconfined compressive strength for this iron ore tailings with Portland cement, and this is G0, which is the initial shear modules that we have had. Here it's I'm gonna go after. This is the idea of the accumulated loss of mass versus also this index that we show that it works. Let me go faster. Here just some tracks or tests with this material with a specific amount of cement, but 2 different densities to see how they do work. We have we can go on. What I mean besides that, that we are also searching for novel kinds of cement that are made of residues in order to raise these tailings, and maybe using even residues that can be used from the tailings. We can do cement, for example, sodium silicate, using the silica from the iron ore tailings. We are doing so, and we have been successful in getting it stabilized. But so this is just the concept of what we are doing. I mean, looking for several residues in order to build brand new cement types that can reduce the price, of course, of the cement and be more sustainable in a sense that you are using the proper residue to stabilize the material. That's the concept. We are also looking at the sustainability, that because so much people talk about sustainability without looking at the numbers. And we are looking at it from the environmental, economic, and also social viewpoints to show if such a material or such a solution is really sustainable or not. So it's some interesting stuff that we are carrying out. Here is a paper in which we produce, for example, a very good line, much better than the commercial one, with using eggshell, for example, at this moment, burning it. And so we produce slaked and unslaked lime with a fantastic amount of calcium oxide and such and so, which is quite interesting. Here is a cement that is made, it was published in 2019, this concept, grounding some glass and putting some of this hydrated lime, and we show here what we get, that you get to permeate, which is a similar thing that you get on Portland cement and so, but that's just some ideas. Here, as I said, there's some paper, this one was published in Geotechnique showing that this cement works for different materials and basically sand materials. Here is the same concept that we have. Let's go on. And this is something interesting because this was a paper that was published in the Journal of Geotechnical and Environmental Engineering in 2021, in which we used for the first time in a geotechnical way, the geotechnical solution, in this case, the idea of alkali activation compared to usual ways without having a real a material. That's in this case, it was sodium hydroxide. We have added to lime and to some amount of ground glass. So, which is interesting from this viewpoint, is that it gets much stronger and fastly stronger in a few days. The material, the stiffness is higher. So it's interesting to see that different cements might get, of course, different results, and it's nice to look at it. This is just a paper that was published in Journal of Cleaner Production 2016. We have some others published in other papers showing this sustainability kind of viewpoint from, when we look at sustainability from the environmental viewpoint, most of the people, they just talk about one of the several points that we have to look when we discuss sustainability. In this case, from environmental, you have embodied energy, you have acidification, global warming, such and so on. In this case, we have been showing what's going on for each one of these for some solutions that we carried out. So this is just to finalize also regarding the commissioning, because in Brazil, all the commissioning of the tailings is being done retrieving the whole material from behind the dams. And here is a suggestion that has been just accepted to be published at the Journal of Materials and System Engineering. Now it's going to be published just in 2023. But the concept of, if you have this problem, with these upstream dams, the concept of improving it in some points, to mitigate it with deep soil mixing or even with shallow soil mixing. And what is interesting from this is the paper that I told you. You can see here, you already have the DOI here, but it's not online yet. These are some results that are interesting regarding static liquefaction that has occurred for these materials. These are gold tailings in a very soft disposal. And here we try to mix in the lab with some different amounts of cement there, since very small amounts to large amounts. And here are some results for this cementation that we have. But what is more interesting, I think, from this paper is specifically are these figures here. I'm going to show you, for example, here you have this dark result in here that are the material without anything with high voice ratio, and it liquefies when you are shearing it. We have added 6 kilograms per cubic meter of cement, and it continues to liquefy. And we see here in this figure here, the liquefaction occurring. But when we put 12 kilos per cubic meter of cement of it, instead of liquefying, you see this red line here, the stress strain, and you see here the dilation, or in this case, the production of negative pore pressure that you have in here, completely different due to a small amount of cement. But okay, in this case, we can see also here that the critical state line does not change. This is interesting because in the end, you get the same critical state line, some liquefy, but this one with, we call, regarding weight, is 1% of cement regarding the solids that we have in here. It turns the material not to liquefy. But when we add even much larger amount of cement, we have here, of course, we have, depending on the amount, 75 kilos per cubic meter, is this blue results here, and 150 kilos of cement for the same material. You have a larger strength, but both come to a unique critical state line whose M is 2.36. This value is much higher than this that you have in the beginning. It is just 1.41. So you change completely the material with high amounts of cement. That's why you have different critical states parameters too. So this is just to finish, and thank you very much.
We have time for questions, comments.
Yes. Thank you very much, Professor Consoli. Your talk was like a classical music. It started from sand and silt at particle level, cemented, traditional ways, more exotic ways, taking us back and forth from site to lab. So thank you very much for your talk. Earlier in your talk, something took my interest when you were talking about the breakage of particles. And I'd like to know your view on something that I've been casually studying in the past years on this site. Myself and a couple of friends, we collected some 11 12 sands from across the board, defected ones and non-defected ones like recently port sand, very port sand, and we subjected them to a range of milling, range of interrupted, like milling, range of energies, and reduce them through a range of particle sizes. So we did particle size distribution and looked into shape and texture. We tried to allow particles to split and also to break on fatigue, if you like, fraction. It seems like, and that's what I'd like to hear from you, because I might be completely wrong, it seems like to me that particularly on the seed size range, we have certain, if I'm allowed to say, universally favored and universally unfavored size ranges. So with universally unfavored size ranges, I mean gaps in the particle size distribution, or particles that almost always break at some point, either under fatigue or under a high stress. And on the other side, we have particles that almost always survive because of their particular shape and size. And also it appears that we have some particles that on particle size distribution and mode distribution analysis, they gain and lose population, so it seems that they are breaking and then reactivating, so, you know, some form of self-healing. And many years back, there was two papers, Tanner and Yotsu, and then we have this Tanner and Yotsu gap that are pretty much about these universally unfavored sizes. Is it something that you think possibly true, or?
Unfortunately, I don't think that I can respond. I need to do much more because we're just beginning at looking at these results. And I just show you the really base without so much analysis for it. We recognize that we have some failure. We have tested some other materials that they are much more fragile than these quartzitic sands and such, and so you have completely different results. But the number of contacts that you have, I think that makes the whole difference. If you have, I mean, something where you have the coordination number, the number of contacts is higher, you are going to break much less, but of course, the shape of the particle, the size of it, and all these kinds, and basically also the mineral, they are gonna make the whole difference in the end. So at this moment, as I said, I don't have a response, a universal response, but for what we have seen up to this moment, the coordination number is fundamental. That's what I can tell you. Thanks.
Thank you. Other questions, please?
Many thanks, Professor, for the excellent presentation. I was wondering if you could give us some clues about the composition of the tailings material. You already mentioned that it contains iron. I'm wondering if there would be some long-term interaction of these of the composition due to the composition of the tailings.
Oh yeah, that's also something that must be searched, because we can find in some places that the tailings are there for a long time in a reservoir, that it looks like in some places, depending on the material, such and so that they are stick together to some bonding that it was not there previously. So possibly, depending on the mineralogy, chemistry, or thing that you might have for after some time some kind of bonds being raised. But as I said, this is an idea that has not been searched by myself. I have seen in some cases, but I didn't go and collect and went to start studying the minerals and such and so. So it might have in some cases, I'm sure that it's going to occur, but it depends on, as I said, chemical reactions, the mineralogical mineralogy that you have over there. You might have possibly, yes.
Thank you, Professor.
Thank you very much, Professor. So I want to ask one aspect that in the first study you have shown, where the critical straight lines were not unique at the end, especially after the high stresses. I want to ask, does the particle crushing or the particle breakage factor was taken into account after the test? Also, what is your opinion that when the particle breakage occurs at a certain stress level, just beforehand there is also a particle crushing factor as well. So does that affect the critical state lines as well or not? Thank you very much.
On those cases specifically, we have not had any crush of that material. So that's not due to crushing those different critical state lines in the specific volume. That's not due to crushing, I can tell you that, because we have seen after and we didn't have any crushing. The size of the particles was kept the same. The maximum confining stress that we have used before shearing was about 400 kPa. So it was not even near the amount of pressure during isotropic compression, or even after, during shearing, we didn't have any kind of breakage. So what's the second point?
My second point was, does the particle crushing also affects the critical state lines in the location, especially if we start adding additional factors into the main site?
Yes, it does. We are going to publish, we already submitted a paper showing that, but it's not in here.
Thank you very much, Professor.
I've got one question. So, with reference to the fabric and in situ rearrangement of material following processes for fabrication, how is this taken into account in the testing?
Well, we are studying at this moment. I have a few PhD students that are looking at the compaction energy, and when you compact it at, let's say, the optimum moisture content, maximum density for standard energy or for modified energy, or as it happened in the field, sometimes you cannot get the moisture content that you wish. It's higher or it's smaller than that. What's going to happen for this material? What I can tell you is that that makes a difference. You have still we have not published. I have results where we're still discussing it, but we have carried out plenty of these results in which it shows that this structure also is very important for this silty sand material, yes, as Professor has told us before. For other materials, also for these tailings, it's quite important, even though they are non-plastic or like that. You might have silty and even some small amounts of clay size, but not clay mineral, that is clear. So it's non-plastic material, and even though you have a huge influence of the molding structure on the results, stress, strain, and strength. Yeah.
So I would like to invite President of Sakarya Chamber of Civil Engineers, Semih Uçar, to present our certificate of appreciation to